Okay, we're going to go into chapter 11. First section is 11.1 and describes what we call a sequence. Sequences, okay? So a definition, and it's a pretty easy concept to understand. A sequence, why am I, okay, it doesn't look right, is an infinite, and when we use the word infinite, by definition, what that means is not finite. To be finite means you can associate a count with it. I have seven, whatever. I have seven people in my house. I have 3 days to do whatever. If you if you're not finite, you're infinite. And I think you have an understanding of the concept. Some students get confused by it. They kind of think of it as a number. It's not. Ordered, pretty self-explanatory. List of it'll be real numbers. I'm just gonna put numbers. So this is a list of numbers that maintain a specific order, and there is essentially no end. And I'm going to put this here, we call the individual numbers, we call those the terms of the sequence. That's a word that you'll hear a lot. So there's different ways to represent these things. Sometimes you'll see them, I'm going to put notation here. Sometimes you'll see them listed out. So there's a definitive starting point, but it's because infinite, there's no end, and we represent that with the dot, dot, dot. So the first term we call A1, A2, A3, and this keeps going, right? So these would be actual real numbers in a live sequence. And one thing to point out, you notice, obviously we can all count. 1, 2, 3. You can think of this almost as a function where the domain are the integers, positive integers in this specific case. Function whose domain is the integers. In other words, if I think of 1, 2, 3, 4, 5, etc., these values, which we'll call the index, if we think of those as sort of the inputs, they're providing the individual values. So that's a way to think about it. So a few ways to represent them. Typically, if you see this type of thing, it's shown with this set notation. That's one way to do it. So what you would, if you saw this, excuse me, you would see, I'll make a really simple example. 246. So the reader is sort of expected to interpret the pattern. Okay, so 246, you would assume that would be 810, etc. 246, 810, etc. Another way, more notation. I'll use this same sequence in all the examples of the notation. Is to use the same bracketing, but rather than list out individual terms, what I will use is a formula for the individual terms. So I'm going to say 2n. So this is a possible representation. Oftentimes what is done, the counting, the n, is called the index. And you might see the starting point, and of course there is no n, so we use the infinity symbol, but the index starts at 1. So that's your counter. the counter is 1, 2, 3, 4, 5, 6, etc. It doesn't have to necessarily start at 1. 0 is also common. 0 and 1 are the most common. In fact, you seldom see something else, although there's no restriction on the starting point. So if n is 1, or the starting point of the index is 1, the count will be 1, 2, 3, 4, etc. The terms are 2 times 1, 2 times 2, 2 times 3. So this is the same sequence. Okay, this equals this. And this is very common because it's a nice compact representation. Also, you might see, and this is actually, I shouldn't say the most common, but also very common, is instead of using this sort of heavy notation, is we're going to just say the nth term and give it a formula. So we'll say an is 2n. Okay, so the starting point of the index is not always given. So sometimes, you have to make assumptions or whatever. But we try to, when I give you things or the book gives you things, we try to be as explicit as possible. So again, there's an index, which is a count. It's a counter. It doesn't have to start at 1. It oftentimes does. And the individual terms are essentially a function of that counter. Okay, so let me write down a few more examples just to get a little practice in. And what you'll see is some of the homework problems they're sort of like little puzzles where they're asking you to, for example, let's do this. Let me write down an example of a sequence. 1/2, 2/3, 3/4. And this is sometimes what you'll see, right? Maybe can I discern a pattern out of this, right? So assuming the count starts at 1, well, 1, 2, 3, it looks like the numerator is just the index, the counter. And I see 2, 3, 4. It's really the same, but I'm starting ahead 1. So sometimes you'll see, we won't do this a lot, you'll see this sort of thing, which really is this. Okay, but I actually have, this is completely generic. I actually have a real life sequence here where I'm showing the first 3, ... and then I show the formula. This is the general term for any n. The nth term is n over n plus 1. Again, I could also represent the same sequence this way, which would be preferred. I mean, this is a little heavy, takes up a lot of space, etc. But I think this is better. We'll show the generic formula, the general term, and I'll specify the start and end of the index. So these are, of course, the same, right? If I'm going to start at 1, my first term is 1 over 1 plus 1, that's 1/2, and so on. Or you might just write the formula. These are essentially the same, although this is a bit more descriptive because it explicitly states where you're starting. Okay, so pretty simple. So I want to give you a little bit more complicated one, and I'm going to do actually backwards. I'm going to start here. I'm going to go this way. So I'm going to say the nth term here is -1 to the n, and then I just have n plus 1. So this is what you call an arithmetic progression, meaning I'm just going to move up 1 through each term. This is what you call a geometric progression. This is going to go by powers of 3. So this will go 3, 9, 27, etc. But I want to point out this guy, this -1 to the n. Think about what this does, right? If n is going 1, 2, 3, 4, etc., what is the -1 doing? Well, we know that even powers of this will be positive. That's a 1. Odd powers of this will be negative. That's -1. So this is sort of what I call a flip-flopping device. This or an alternator. This essentially what this is doing, right? Your number is here. What this piece is doing is alternating the sign from positive to negative. So if my index starts at 1, My first, let me do this real quick. Sorry. Just to show this possible representation. Sorry about that. It's a doodle. So if I were to write these out, really, like I said, the actual sort of numerical value is there. So I'll have 2 over 3 to the 1, right? And then I'll have 3, let me just write them out, 3 over 9, 4 over 27, etc. But this thing is alternating the sign. And since I'm starting at 1, I'm going to start with a negative. Then the power is 2, that's a positive. The power is then 3, also a negative. So you'll see this is very common, the alternator. You're going to see that quite often. What you might see also is you might see -1 to the n plus 1. So if I were to do that, if n is starting off at 1, the power is starting off at 2, and these would all be changed. Okay, so you can play with these things a little bit. So again, the beginning homework problems, they just have you really experiment with these things a little bit. They have you list, they'll give you this and ask you to provide this, and vice versa. So if they give you this, this should be no problem, but it's good practice. If they give you this and you have to produce this, they can be, little puzzles, little brain teasers, and there's no real way to explain to someone how to do a brain teaser. But what you should look for are a couple things. One is the alternator in play. Number 2 are the values progressing arithmetically. Is it an addition? N plus 1, maybe it's n plus 2. Or are they progressing geometrically where they're powers? So those are very common elements of these things. And they'll be good problems for you to get acquainted with sequences. Not a real difficult idea. It's a little bit notation heavy. That's a big part of this chapter. I find students are a bit overwhelmed with the notation. So do the problems and focus in on using good notation so that you're comfortable with it. Okay? Let me stop for a quick second. Okay, so a very important part of this section is understanding what we call the limit of a sequence. So I'm going to put 2 sequences down. They're really, really simple and they're crude, but I like to use simple things when introducing a new concept so you can focus on the concept. One of them, this is almost mindless. Let's use 2n, so it's not too bad. And the second one, I'm going to call this bn, just so it's different. Will be 1 over n. So what does this one look like? We're going to assume n starts at 1, 2, 4, 6, 8. And you notice I put 4 terms, and previous ones had 3. I don't believe there's any set rules. I think the prevailing notion is you put as many down as needed so that the reader can interpret the pattern. So I think 3 probably would have been sufficient, assuming we didn't have this. So if I have 1 over n, I'm going to write 1 over 1, which you might be saying, why is he doing that? And I'm going to put more here. You'll see things like, normally we would, scoff at this, 1 over 1. But with sequences, sometimes you'll see things like that because it allows the reader to establish the pattern better. If you just put 1, that's just as well. But if I have a 1 and then I have fractions, somebody might not see it as clearly. But I think it's very clear what the pattern is here. Okay, so this is the idea. Let's talk about these 2 sequences. Let's think about what the first one does in the long term. And it's fairly obvious. This will just keep growing and growing and growing. Okay? As opposed to this one, what does this one look like it's doing? I got 1, I got a half, a third, a fourth, a fifth. So what this thing will keep doing is getting smaller and smaller and smaller. If I write out 1,000,000 terms, I got 1 over 1,000,000. So this thing is what we call approaching or converging to zero. Okay, and what we would say is the limit of this sequence is 0. Up here, this is not converging to anything. This is growing out of control. So this has no limit. The limit of this sequence does not exist, would be the terminology. So let's talk about this in terms of limit language. Right? When we talk about limits, we never equal 0 for this example. We could write out terms until, the next 4th of July. We're never going to get to 0. But when we say it converges to 0, what that means is we can get as close to 0 as we feel we need to if we just keep going. So if I feel like I need to get close enough to 0, maybe I'll write them out till the 4th of July. But that is the essence of a limit. So I'm going to write out this definition. And it's a little wordy, as all limit definitions are. But a lot of the language is the same. If you know about limits of functions, this is sort of the same, but not. The limit of a sequence. And there's good news coming. And I'm going to write this generic sequence, this AN, is L, in this case 0. Written this way, and this should look familiar. Now, one thing you'll notice, the N is always said to go to infinity. So, that's the count. So as N goes to infinity, in other words, as the list goes to infinity, the limit of the terms is L. And this is really the same notation you'll see with functions. However, we're always going to go to infinity. We would never say as N goes to 2. If N goes to 2, that's the value. That's not really useful conversation. Okay, so this is true if we can make AN, that means we can make the terms as close to L as desired. I always find that language funny. Who desires this to go to 0? It's a pretty lame day. How so? How can I make, say you want this within a certain, distance of 0. How can you make that happen? Just get enough terms by making N sufficiently large. Sufficiently. So I could say, in terms of this example, I could say I can make these as small as I want, and they don't all go to 0, obviously. But I can make the terms as small as I want just by making enough of them. Just by having N large enough, just the nth term is big enough, I'm as small as I need to get to, as small as I need to be. Now the language that we'll say, you'll hear this a lot, is that AN, the terms, 1 over N, for example, converges. This is a word we're going to get used to. Converges to L, in this example, 0. 1 over N converges to 0. And if no limit exists, as in the top example, limit does not exist, we say the sequence diverges. The sequence. Okay? So, it doesn't always, this is an example. This isn't the only way a sequence will diverge, but this is common, and this is applicable to this example. We can say that it goes to infinity. Now you can have sequences that don't have a limit that don't necessarily go to infinity as well. For example, if I go back to the flip-flopper, say I had -1 to the n, that would be +1, -1, +1, -1, +1, -1, etc., right? Just go back and forth. Well, that's not going to infinity, but it's certainly not converging. So this is a common way to diverge, but not the only way. Just keep that in mind. Okay? So there's good news, like I said, and I'm not going to go through the theorems. I'm not gonna put you through that. I'm just going to cut to the chase. In fact, I want to check my notes for a second here. Yeah, I'm not going to do that. I'm just going to write this out in plain English. So you will be asked. In fact, I'm going to put an example first. A common problem, and this is in the homework, is find the limit of a sequence. So I'm just going to pull one out of the book. 3 plus 5n. No, I don't want to do that one. Yeah, this is fine. I'll just make it up. Okay, so here's what you don't do. You don't go back to this idea. You don't list the first 60 terms and try to figure it out. The good news is this. We find limits of sequences by treating them like functions. And there are theorems that you can look up in the textbook that justify this, but that's good news, because to find the limit of this as n approaches infinity, which is always the case, like we said, we treat it just as if it were f of x. Okay, so what I'll do, this is what I want to find. I should have put the limit here, actually, but so the problem would look more like this. Well, maybe not the case. Either way, you get it. This is what we're finding. I think maybe the wording in the homework is something like this. Find the limit of the sequence. So think about that. It's understood that n goes to infinity. They might present you the sequence this way, but it's understood that this is what you're doing. And again, I'm going to treat that just like it's a function. So this is a rational function, or it's not, but if it were, I can compare powers. They're the same. The limit would be the leading coefficients, 5/3. So if I were to list out a million terms of this sequence, they would be getting arbitrarily close to 5/3. So that's really good news, because essentially you already know how to do these problems, right? You just take the limit as if for a function. Just keep in mind it's not the same. A couple things to mention. You might run into this guy. N factorial. This is called a factorial, this exclamation point. And this is a descending multiplication, is what I typically call it. So if you have 4 factorial, you got 4 times 3 times 2 times 1. So you can write n factorial this way. N, well, I'm going to descend all the way to 1. N times n minus 1 times n minus 2, ... These are multiplication. You might see something like that, right? That's n multiplied by every integer down to 1. 4, 3, 2, 1. Okay, you might see that. So let me get a drink quick. Okay, a couple theorems that I am going to present that'll help us with problems. Something stuck. It's still there. What is it? Yeah, let me write it and then explain it. Absolute write that down and I'll explain it. I'll explain it by example. So what this is a tool, this theorem is a tool that enables us to handle that flip-flopping device, the alternator. For example, say you had to find the limit. I won't write find the limit, but say AN is, I'm going to go real simple again. So this is the, the 1, the 1/2, 1/3, etc. But it has the alternating device. What this theorem allows us to do is, in some ways, in some cases, almost ignore that. So in other words, if I take this limit, the absolute value, well, if I have an absolute value, the alternator is ignored. It vanishes, right? It doesn't matter if it's +1 or -1. I'm taking the absolute value, it's 1. So it essentially vanishes. And if it were to vanish, this equals 0. So if this limit equals 0, then this one is 0. Okay, so this theorem keep in mind one thing that's important. This is only for limits that go to 0. So if this had gone to 2 or whatever, none of this would apply. Also, if I have the limit of some number, I'm going to call it C, a constant, to the nth power, if C is greater than equal to 1. Think about if this is 2 to the n, what am I going to have? 2, 4, 8, 16, 32. It diverges. Okay, what if I have C less than, and notice it's absolute, so it could be negative as well. Negative 1/2. So think about if I have 1/2 to the n. Well, then I have 1/2, 1/4, 1/8, 1/16. That converges. And it converges specifically to 0. Just wanted to check something quick. Something bothering me here. Give me a second. Converges to 0. You know what? Yeah, this is not right. This should be strictly greater than 1. If C is 1, it'll stay at 1. But that's never going to come up. Converges to 1. That's never going to happen. So if you're greater than 1, your powers will diverge. They'll go to infinity. If it's less than 1, or between -1 and 1, they'll just get smaller and smaller and go to 0. Okay, so that's very useful, and it's probably pretty clear. I think maybe I didn't even need to really tell you that, but it's going to come up. Okay, a few definitions. We have, and these are simple, actually, definitions, almost self-explanatory. But I'm going to say that a sequence, and I'm just going to call it AN, is increasing. What do you think that means? Well, if the terms are just getting larger, right? So mathematically, we would say this, right? Each one is greater than the last one for all n. And what do you think's next? Decreasing. Now, I want to bring up an important point, is that something that you might see is what we call eventually increasing or eventually decreasing. And what that means is that maybe the first, so let's use an example for eventually decreasing. What that means is that the first couple terms might increase, but at some point you go off the cliff. At some point it breaks and then it decreases, you know, the rest of the way. So that's called eventually decreasing or eventually increasing. That might come up. Also, again, pretty simple idea. A sequence AN is what we call bounded above if there is some real number, and this is the notation, I'm going to call it big M, such that every term is less than that. So in other words, it's like a ceiling. It's an upper bound for all n. Bounded above, right? If there's a ceiling, if there's a value that none of the terms can obtain. And of course, what's next is bounded below. Same idea, there's a floor. If there is some real number such that we're greater than for all n. Terms that might come up, okay? So this is important information because we're going to talk about what we call series in chapter 11, and series are often misunderstood. A series is actually a very special case of a sequence. Okay, and we'll talk about that in the next section. Okay?